Today we have a special visitor, and I must say special because everyone working with wood adhesives should know the name Antonio Pizzi. It is written with golden letters, I must say. We all know Antonio, not only for his extensive work, but as a person and collaborations in different projects and activities all these years. He has published more of 1,000 research articles, more than 10 books, 12. We cannot count anymore. And has been famous with his work on synthetic and bio-based systems for wood composites and other applications. He is a recognized researcher, member of the International Wood Science Academy, many distinctions and many prizes over the year, even by the European Commission. I should not say more about that. I will let Antonio to guide us through his vast experience the next 40 to 45 minutes. So, Antonio, the floor is yours. And after that, the questions will be coordinated by Torbjörn, who has a full picture in Zoom. So, thanks a lot.
Thank you, Sergius. I'd like actually to make, one point, first of all, the presentations at the moment is actually fashionable to talk about bioadhesives, and there is a lot of publications and a lot of formulations that are actually proposed. Now, what I actually proposed in this presentation are only formulations that are actually feasible in industry, because there is a lot of things that are actually good for academics, but is not actually translatable in industrial thing. So we just start. Okay. Now, as you know, I actually worked, originally when I was young on tannins, and also still working now. So in the past, first we're doing actually a first story. Tannins and lignins were the main materials that were actually aimed for, bioadhesives. The polymeric nature actually strongly limits the amount of formaldehyde to all its use as a hardener. So it means already is a great advantage. Proteins already were looked at, and as well as many other materials today. Tannin adhesive resins by new technology, so non-traditional, no formaldehyde, protein-based adhesives and resin, unsaturated oil-based adhesives and resins, lignin resins and adhesives, hybrid, glycosylated, lignin, or other new systems, or cross-linking lignin, and carbohydrate adhesives that are all in the microscope, for bioadhesives. Now, the tannins were the first one that were developed commercially, and they're still commercial, at the beginning of the 1970s. They're commercial in South Africa, they've been commercial in Zimbabwe, they've been commercial in Chile, and they are still commercial in Australia. They extensively used for particle board and similar composites, and then for plywood, and finally for glue and finger joints. I will talk here only for panels. Now, their development and improvement, both research and industry, was based for many years just on the use of paraformaldehyde in much smaller proportion, about 1/10, than what is actually used in synthetic resins. Bark of many trees useful for tannin extraction and tannin adhesives. Spruce, all over Europe, radiata pine, in Chile, Spain, New Zealand, maritime pine, Douglas fir, Pinus brucia, and many, many other sources. They're all cultivated species. They're all cultivated species. There is not cutting of natural trees. The only one that is actually naturally a resource is actually quebracho in South America. But all the rest is a cultivated species. Now, there an example of a trial of tannin adhesive in 1994 is in Germany. And the tannin used is pine plus pecan. Naturally, with the hardener was paraformaldehyde of hexamine. There you can see the board in a balsam plant that actually controlled, for thickness by the operator. And the first question that every people ask me, How is it possible to have a system that is based, on water, that actually to have a faster pressing time? There were two systems. One system that wouldn't advise anyone to use, we used initially, to use actually tannin in powder, to the glue blender. And another one that was used later that is actually very effective to put, to be in a heat exchanger, in the line that transport the chips, the chips to the forming station. That actually was very, very effective and is actually still used. Now, that is in Chile. Now, that is a very old plant that actually was in operation for 10 years before the plant was closed because it was too old, to make actually a pine tannin bonded particle board. It was a Chiguayante in Chile, near Concepcion. Now, exactly the same plant. You can see it's a very, very plant, but it actually worked very nicely for 10 years and produced both for 10 years with radiata pine tannin. Now, that we work in Africa, that is a melamine board, was actually at the time, was a long time ago, that's a very good formulation of melamine board, and that is a tannin board. And both of them, they're actually industrially made, and is after 15 years exposure to a high UV area at 1,500 meters of altitude. And you can see actually the difference of the resistance of the surface of the two boards, and particularly of the edge of the two boards that are actually not covered at all. Now here, I'm sorry for the noise, is a planta of pine tannin adhesives in Chile. It is in a very big factory. Arauco is the company, a very big company, and now Arauco actually started to use tannin adhesives, import tannins. They wanted to actually extract, in Chile, but actually they use at the moment imported tannin. You can see there the ply that is actually being glued. And you can see immediately after pressing that is actually an effect test, the type of wood failure that is actually obtained. I remember, the factory manager told me I didn't believe, in a natural adhesive, in bioadhesives, but now I definitely believe it. It's actually very good. Now, there is, other than paraformaldehyde, there is alternative hardeners. Methylated natural paraffins, they're good, very good, but too expensive. Oxazolidine, good, but expensive. Glauxal, hexamethylene tetramine, and then citric acid, ionic liquids, 3-exudates, etc., which will speak, in contest, of all those other things afterwards. In presence of highly reactive tannins, hexamine, the famous hexamine, does not behave as a source of formaldehyde. Parent formaldehyde emission equals 0 to 0. Is a trick, fundamentally, but it works very nicely. And that you can actually see. This was something that was actually first mooted in 1948 by a very famous German chemist, Hulsch, that actually say that hexamine actually rules out a species like that. And the fact that he actually had two carbocation, no one actually believed it, when he, in consequence, was correct. Because the correct species is the one that is indicated there. Is in amino methylene basis, and is extremely reactive. And actually, it forms a bridge of this type with the tannin that is actually stable, and the NH, that is actually free, it contributes to absorb the formaldehyde that is emitted by the wood heated itself. So the emission is 0.0, effectively checked. Now, the system with hexamine that you've seen, it is used by steam injection presses in Japan. This was used in actually Quebracho hemimosa tannin, steam injection in 2 bouts during the pressing cycle, and is still used in Japan. And you can see here that actually very, very thick, in fundamentally 40 millimeters thick or 120 millimeters thick, that then they were cut in beams. And you can see the dry internal bond strength in megapascal is actually very good, is actually better than the Japanese standard. The 24-hour cold water swelling is actually better than the Japanese standard. that is actually the most severe that exists still. And the formaldehyde emission, was actually 0.0. In the pressing time, if you actually look at 300 seconds and 300 seconds, you know what I mean, is actually very good for boards, of 40 millimeters, 120 millimeters big. That actually what they cut the board in these beams that actually used for the sustain of Japanese wooden houses. Now, then going back tunneling autocondensation, the Japanese actually consider actually this is an environment, but it's only interior. They want actually something that could take much better actually moisture content. And you can see actually here the internal bond of boards manufactured, with only some silica or silicates, I'm talking about 2%, 3% to this, that actually give autocondensation, self-condensation on the tannin. That pecan tannin, that is pine tannin, that mimosa and quebracho. In the case of mimosa and quebracho, to mean a high amount is needed just to pass the DIN standard that is now the European standard. Tannin adhesives are 95% to 100% natural, they still are, contain no oil-derived products. So they are now non-toxic adhesives satisfying tough Japanese standards. They use waste material, the bark, the spent bark used for mulch in forestry nursery, or is burned for energy, depends on the country. This was in Chile, in South America they do that, and this burned for energy that was in South Africa, what actually was done. Now we're talking about other adhesive other than tannin, bio, soy protein, and soy flour adhesives by tannin addition, by sodium periodate, sodium persulfate, specific oxidation, especially for soy flour. Now these are actually much more recent formulation, but promise a very, very good utilization, practical utilization. If you take a carbohydrate and you treat it with a sodium periodate, what you do that cut the carbon to carbon bond and you form two aldehyde groups. Two aldehyde groups can be actually go to carbohydrate cross-linking itself, or the aldehyde can react with other species to form cross-linking. And also the protein itself, the protein actually is cut and produce actually aldehyde groups. So if you got soy flour, you can actually obtain actually a very good adhesive in this way. Now, in the case of this work was initially initiated by the Forest Product Laboratories in Madison, Wisconsin, but we actually clarified the chemical reason why it actually worked between ourselves. Now, for instance, you produce aldehydes that then are cleaved and then rearranged in glyoxal or other things. But you also got to be much bigger non-volatile aldehydes that are actually quite more convenient. The same with sodium periodate or persulfate, you can actually do the lignin. Lignin cleavage actually give you actually this. And with tannin also, you actually can have oxidized sugar reaction. The tannin generally is a tannin extract. It contains sugar. So pieces of hemicelluloses that can be used, by peroxidation, to obtain, aldehydes that then cross-link the tannin. Or you can add a sugar as well, starch if you want, and actually do that, by oxidizing or pre-oxidizing the sugar that you've added. You've got also specific oxidation approaches used by dial-dyed starch. Now, dial-dyed starch is produced industrially in China, for instance, but it also can be produced easily in a laboratory or by anyone. The industrial one is actually produced by using hydrogen peroxide. And this was a system proposed, by Chinese. They use, potassium permanganate to form the 12 dye groups and actually cross-link the starch with urea. There is no formaldehyde actually here. It gave very nice adhesives. Also, you can react, urea with glyoxylated lignin, so pre-glyoxylated lignin and starch. You can have a mixed adhesives in which the urea is the cross-linker that is also resistant to water, when the first one, the top one, is not resistant to water. Then came, the utilization of tannins, with actually proteins. Now, first was protein and soy flour adhesives and tannic acid. Tannic acid is not the traditional flavonoid tannins, as you know, like mimosa, like abbraccio, is actually an hydrolyzable tannin. And you can actually see by coordination, this system still needed a hardener, like hexamine, to actually harden it. But the next step was actually much more interesting. And we found, for instance, that soy protein and soy flour condensed with tannins with no hardness. Now, the reaction happened at 80 degrees centigrades. So what actually you got to do is to have a fraction, and here's a fraction of a protein that reacted actually with a flavonoid tannin at 40 degrees centigrades, not to actually cross-link it completely, and then actually used for ploughed. And you can see here the results, the dry shear strength, the wet shear strength, the bony shear strength. When the reaction is done at 40 degrees centigrades, you actually got these results once you press the plough at the normal pressure you want. What it means, if you increase the temperature, then you will have nothing anymore because actually started to cross-link. That means you can actually press boards at a temperature that is actually lower than what actually you press today. You get no aldehydes whatsoever, and you actually got just the protein and the tannin. It works very well and is very, very easy to use. We actually propose this as a concept, more than actually a funnel, because it can actually, you can superpose actually the system to a lot of other systems that actually use today. Then you can have a mixed tannin lignin, glycosylated, pre-glycosylated lignin, tannin hexamine, and you will have actually a mixed cross-link polymers of this type. That also works quite well, but you got to pre-glycosylated lignin, and you're still using hexamine. Then you got citric acid. Citric acid is actually very famous at the moment, was for the first time proposed by Professor Kenji Umemura, that I know is a good friend as well, and was us that actually explained for the first time, what was the reaction. It reacts with the carbohydrates. You can use that is citric acid with the carbohydrates, so it cross-link the carbohydrates, and it cross-link the lignin as well. So it means that you actually put citric acid on veneers, you can explode only with citric acid. It will actually cross-link, between one veneer to the other veneer. It's no problem at all. And it can be used, of course, to be more effective with sucrose plus citric acid against Kenji Umemura. And you can produce, 5-hydroxymethyl furfural. You can have furfural. The citric acid itself reacted both with the furfural as well as the glucose oligosaccharide. There is a problem on this one, a problem that no one realized. Me too, I didn't realize at the beginning. And then when we realized it, we were shocked. And is the following. Citric acid renders the glue line in contact with very acid. Data indicates pHs 0.8 and 2.1. So the international bonding standards for wood do not admit adhesive that after curing have a pH lower than 4, as the wood interface gets degraded by hydrolysis with subsequent but not immediate joint failure in the wood. This declassifies citric acid-based adhesive system for wood, such as citric acid alone, monosaccharides plus citric acid, and other similar ones. But we found a remedy for this, because the system is too interesting to let it drop. Now, we can have, for instance, 45 melamine urea formaldehyde and phenylformaldehyde resin with citric acid. And melamine or melamine UF resin, when you add 3.3% of hexamine, is a strong buffer that actually maintains the pH well above 4. So you have the citric acid that contributes to the reaction, react both with the alcoholic group formed, the hydroxyalcoholic group formed by the formaldehyde, as well as the melamine itself. And that can be applied, and that is the system. It was developed, in 1986 for acid-setting phase resin. You got the morpholine, that molecule there, plus weak acid forms a complex that is actually quite stable. Then when you actually put the complex in a glue and you put the strong acid that actually cures the glue, in this case would be strong acid would be actually the citric acid, then you can have, the complex reforms. It's not with a strong acid, with a weak acid, it's with a strong acid. That means only the weak acid rests, and consequently the pH on the glue line is actually much higher. So there is not very much problems to actually use this. And the system is a system, sorry, I'm going back. The system can be used, and it has been used successfully for soy adhesives. The publication is come out actually last year. And, for tannin adhesives, so tannin, citric acid, nothing else, is actually at the moment, in press. It has not yet come out, but it works. It does not work with glucose because the amount of citric acid needed with glucose is actually too high to actually have the effect, but the effect is not enough to bring the pH higher than 4. Then, naturally, hydroxymethylfurfural, furfurylalkyl, and other furanic adhesives are also very much interesting, and there is a lot of research actually being done on them, at the moment. Most interesting is something that came from Cameroon. The African trees bark exudate used as natural hardeners of tannin in this case. Now, the exudates, obtained, like you obtain latex, for instance, from a tree, or a number of African trees, contain actually furanic moieties that is attached to that. And when you actually press this material together with a tannin, for instance, or something else, what actually you do, you detach the some of the furanic moieties from this hardener, and they hardens actually the system to actually have a mixed carbohydrates and tannin system. This works actually quite well. The people in Cameroon are still working on it, quite well, and it's actually a very easy, very feasible system that is totally bio. Then you can have, this was developed for totally different reasons, but is actually usable for wood as well. Tannin with triethyl phosphate, gives adhesives that actually can glue Teflon, for instance, to metal, aluminum, or steel, and actually is a patented system with the tannin. But one of the biggest producers of non-stick pan in the world, that is Tefal, is a French company, and it works very well. This is published, but patented that. But it can be done with lignin. It can be done with lignin as well. I haven't got the film for this one. You can actually just see the picture, of the pen actually done with the system. And with lignin, that is not patented, so everyone can use it. You can see, the contact angle of the drop, when the system is not used and the system is used, and without treatment and lignin triethyl phosphate treatment, you see it's very good. You can see it maintains actually very well. That is actually free for all. It's not patented. Then we graduated to non-isocyanate forms and adhesives from biomaterials. Forms particularly, but bioadhesives as well, work very well for particle board. And you can use anything. The people actually insist in using sophisticated cyclic carbonates that are actually very hard to open, so they are slow reacting, so not really usable for wood adhesives. And you can actually see you can use tannin, so anything that presents OHs. You can use lignin, presents OHs as well. Glucose, if you want. Soy protein, soy flour. You react with dimethyl carbonates, is something very, very cheap. In aliphatic carbonates, it's got no suckle, is already open, it reacts very easily. And with a diamine or a polyamine. Here's with the diamine was the original one that we used, but also with polyamine. We even arrived to actually put amino groups on a tannin and have tannin, dimethyl carbonate, and aminated tannin. And you form, tannin, non-isocyanate polyurethane, lignin, non-isocyanate polyurethane, glucose, non-isocyanate polyurethane, and soy protein, the same. And the results of particle board are very good. Now, in the case of carbohydrates, glucose, sucrose, non-isocyanate polyurethane. Now, these species, these polymers, you can see actually what rest of the carbonates, that's the sugar, that's the diamine. These species actually be isolated. They form, and it works very well. They work very, very well, as adhesives for wood particle board and plywood. So polyurethane with isocyanate, you can actually carbonate your tannin, for instance. You react with the diamine, and you will get, your non-isocyanate polyurethane used as adhesive for particle board, and it works very well indeed. So you go an example see as surface finishes. You can see actually without the surface finishes, with the surface finisher, that was the original use of the non-isocyanate polyurethane, on appel NIPU, non-isocyanate polyurethane. And you can see it actually works quite well as a coating as well. Then, as I told you, you actually react with the carbonates, the tannin, react with ammonia, the tannin. So we actually introduced the NH2 groups in the tannin. It's actually quite easy, the reaction. And then we actually got a non-isocyanate polyurethane, that's a urethane linkage, between the NH of the aminated tannin and the OHs or the carbonated tannin. And that works very well as well. It doesn't work for adhesive, it works for coatings very well. There's no problem on that, but it works very well for coatings. You can do the same story with the hydrolyzable tannin. You can make actually natural polyurethane without isocyanates with also hydrolyzable tannin. This is an example of a unit of hydrolyzable tannin, like chestnut tannin, for instance. You can see a glucose core, and the different gallic acid are actually linked to the glucose core. And there is OHs down the phenolic part, and again, residual carbonates, the diamine or polyamine or not amine, and you actually have it with natural tannins as well. Same with lignin. That species we isolated. We had lignin. The carbonated reacted with the OH of some unit of lignin, and the diamine, and the carbonate that has reacted with different part of the lignin or different OHs of the lignin. Even with the aliphatic OHs, it reacts. But these species that you see there has been actually isolated, identified. Then you got tannins, three adhesives. The improvement by hyperbranch polymers, no hardness as well. You can actually see what you get. You got, a branch diamine, it actually can react, to a different, tannin or different other material with lignin as well. It is very, very like by Chinese researchers to actually have the hyperbranch polymers based on urea, based on tannin, based on lignin, to actually have adhesives for wood. It's a relatively simple system. The problem is one must not go to click something that is too hyperbranch, because in the case you actually do too many reactions to actually be worthwhile to implement in industry. But it's an interesting system. Then urea, is also bio. Urea glycol adhesive is an example. If you use actually ionic liquids, actually are the materials you can see, and actually you can have urea glycol reacting at the same speed as actually urea formaldehyde. The problem is, again, with this, sometimes with the ionic liquid, sometimes when it's homemade, the pH might be too low. Then you got to use a self-neutralizing system, as I show you for soy citric acid. But the soy citric acid, tannin citric acid alone, so are much, much easier a system than to using this. But you can use urea. You can see, for instance, by the DSC curve, the urea glycol resin and urea glycol plus ionic liquid. You can see, okay, as you add the ionic liquid, the heat flows or the energy of activation is actually much lower, and hence you can have pressing time as fast as urea formaldehyde. I show you actually some particle board test results, for instance, with ammonium chloride, 2%, with no hardener. And when you actually use 1, 2, or 3% of ionic liquid, the type of dry internal bond tech you got is actually much higher. At 2%, you got 130, when with sodium sulfate, sodium chloride, you will have 0.80 with a good urea formaldehyde resin. Urea is also bio. Talk about dull dyed starch produced industrially in China, but easily producible in the laboratory or anywhere else, even with hydrogen peroxide. And you can actually react, urea with dull dyed starch in this way, and you will have actually a very nice adhesive or very nice coating. Now, this system, was first actually used by Salih Oktay, that is work for a very big particle board group in Turkey, and is one of the things that actually can be used industrially. I think they actually have trials industrially, but I didn't participate, so I cannot tell you if they were successful or not. But they are working actually on bioadhesives. I work with them on other bioadhesives. Melamine glyoxide resin, type of chemistry species formed. Okay, you can see yourself. You can see the melamine glyoxide resin. They got a very big problem. With chrome nitrate or with paraformaldehyde or other things, the dry internal bond strength is not sufficient. It's not sufficient at all, and is very good instead for paperware lace. That is paper with impregnated with melamine glyoxide resin, and is good enough, for paper impregnation, passed all the tests of the European standards. Then we developed melamine glyoxal glutaraldehyde with 10% ionic liquid, and you actually can see with the two aldehydes, you actually got, value of 24-hour cold water shear strength. That is actually very good. There's no problem from the point of view. But if you want interested melamine, you can think, is actually not natural, but it is natural because it's actually formed by trimerization of urea. So you can say fundamentally that it's actually biosalt as well. Again, this species here was isolated, and that actually for surface finisher, paper impregnated surface finisher, what it gave. So you can see it's a very good results. Thank you for your attention.
Thank you, Antonio, for swift and very interesting presentations. You're still here, Sergio, so maybe you want to say some words.
Yes, I just want to thank you also, Antonio. That is an impressive collection of recipes which show development over the years and future potential, which is very important for the center. We have learned a lot from you, and I'm very happy that we continue to learn. So now we would like to give the possibility for the attendees to ask some questions, and Torbjörn will organize that. From myself, many thanks again.
Thank you, Sergius. Yes, I don't know if we have any verbal questions, but we can start with a written one from Ali Dorier here. He says, first of you to Antonio, that your dedication to expanding the knowledge of wood adhesives, bioglues, and wood-based panels has left a lasting impression, and he will forever cherish the experiences and knowledge that you have shared with us today. He has some questions here. They are, of course, the big and tough ones. What major process changes are needed in the use phase of alternative compared to use of formaldehyde?
Okay. In the case of plywood, actually, there is no real need or change, actually, the installation. In the case, of particle board, what is actually generally reproached, to the bioadhesives is the slower pressing time. I'm explaining to you, in the case of tannin is a phenol, but while phenol melts, the tannin doesn't melt, it dries. So you've got to have water. And when you actually add water, the pressing time is too long. And that was the major problem that actually we had to bring the tannin to a fast pressing time, because the reaction is very fast, but it's dry fast as well. So that's why I showed you, we actually started to add with a screw conveyor, some tannin powder, in the glue. It worked, it was messy, was very, very bad. But we definitely developed a system in which the chips that are resinated with the excess water and tannin or another material pass through a heat exchanger. It takes 4 seconds for the chip to arrive to the forming station, but it's actually very, very fast. It's actually fast elimination of some water, so that you actually got a moisture content that is normal, and you can press at a normal fast pressing time. That actually was the advantage. But then we succeeded. That we take it quite quiet. I actually published a paper on that. Eventually, I'm quite old, as you can see probably from my image. So, I say, because the people ask me, but how you get the fast pressing time? So we kept it quiet. So now it's published and everyone can do it.
Great. I see that he has a second question here. Is there a difference with the use of alternatives in terms of a technical performance? Of course, there are, but you have issues like function in practice, processability, results of use, practice, quality, durability, and others. Yeah, that's perhaps yet another presentation.
There's not really a difference. Not really a difference. The thing is, the problem on natural adhesives, is not really on the technical point of view, because they are used. For instance, the tannin adhesives are used, in Chile, in Brazil. They're used in Australia. Australians are the oldest one. In South Africa, they're still. I think they're still used in South Africa. Yes, in Australia, they've been used in New Zealand. They've been used in Hong Kong, for instance. So there is lots of things that can be used in natural adhesives. So there is not really any difference. The problem is to choose a material that is widely available. That's the reason why starch is actually widely available. So it is actually very, very popular. Tannins, is limited because there is only about 220,000 tons of tannin produced per year, and there is millions of tons of tannins that can be extracted all around the world. Everyone has got pines, they got spruce, they got all sorts of things, but they need actually a factory to extract it. For instance, an example pretty interesting was the Japanese. The Japanese, actually kicked out isocyanates from the manufacture of the very thick boards, and actually was used tannins. They found that the tannins that they were buying on the market were a bit expensive for their taste, so they actually put up in Sumatra 2 pine tannin extracting factories. And they use their own tannin, they use still to manufacture, the very thick boards that they use in Japanese housing. So one has got to have the courage, and there is actually companies that started to have the courage to actually look at setting up extra tannin extraction factories, because they are not actually very expensive factories. There is actually, I know, a small industrialist that is doing that, just that in Australia, for instance, and it's okay. But if you can't, or you don't want to do that, then use another material. Use lignin, use soy, use starch. There is all sorts of bio raw materials that can be used successfully for industrial implementation. Don't look too much at lots of publication that comes out today from on complex systems of making adhesives, bioadhesives, because they are too complex, to actually pass into industry. What I presented are actually quite simple application. You can build on it and do things different on the basis of what I presented, but they can be used, quite easily by any industrial situation. There is not very much difference. The supply is the most important thing in bioadhesives.
Thank you for that answer. We have a hand here from Linda Fogelström.
Yeah, it was actually me raising my hand, but I'm sitting next to Linda. I'm Eva Malmström. So thank you very much, Professor Pizzi, for a fantastic presentation. Very awesome. So I have two questions. The first is with regards to using biopolymers or bio-based sources, industry sometimes claims that variability is a difficulty, that the species may change depending on growth season and where they are grown and so forth.
That is one of the problems I encountered when I was young and I was doing the tannin adhesives. Now, let me explain to you. In the case of the tannin adhesives, extracted, you can use the tannin as is, for a tannin extract as is, or you actually can undergo a system to eliminate the great variations that you can have. Now, or you actually keep a reasonably constant, the system of extraction, or otherwise, and I can speak only for mimosa and quebracho tannin, or you use actually a system, I call it the South African system because it was invented in South Africa, in which you actually treat, first with acetic or maleic anhydride, then with caustic soda, and you digest for about 3 hours, and it works extremely well because I remember mimosa tannin extract, I did, hundreds, batches, big batches. You come in at viscosity of 3,500 centiposes, and reducing the viscosity in the system anything between 300 and 600 centiposes, so perfectly usable. But it works very well with mimosa. It works very, very well with the quebracho. So with non prosanidin tannins, but in the case of pine, for instance, or spruce, it doesn't really work. You can use it, but it's not worth it. You're making an operation more for nothing. You can use it like that, especially because pine, spruce, this type of prosanidin tannins, they're very, very reactive. I remember, I went to Chile actually to actually use pine tannin because the Americans were saying that pine tannins are too reactive, cannot be used. And I had to prove them wrong, and I proved them wrong because the factory in Chile was in operation for 10 years, before the closed because it was too old. So, you don't need anything because the variations, nonetheless, they actually smooth it. Because if you consider the amount, say, 8%, 10% of tannin you put on a particle board is nothing in relation to the wood. So the thing that you got, it doesn't really do anything bad. The only thing that can actually be bad is the viscosity. In the case of pine, the system is simple. Don't put, as we were doing, a mimosa and quebracho 50% solids. You put it at 45 or 42, if you want, percent solid. And actually, when you actually glued, you make the heat exchanger, the water goes away, and all goes fine. So it's actually stupid, the solution. It's a mechanical solution, but it works.
Very good answer. Thank you so much. And my second question is also related. Now, when there is such a big strive to go to bio-based resources, what do you think is the largest hurdle for the industry to actually make a step towards using bio-based adhesives instead of the fossil-based?
It depends what they want to use. As I say, supply is an important thing, but starch. In China, the starch is produced industrially, so you can actually buy it. So I didn't even know they was produced industrially till my Chinese colleague, they indicated, and I used it myself. It works very nicely. But otherwise, you can oxidize the carbohydrate, polymeric carbohydrates, whatever you want, even cellulose you can do, or hemicelluloses, with periodate or persulfate, or even permanganate, or if you really want to go on the cheap, you can use hydrogen peroxide. I wouldn't have particularly advised the Chinese use hydrogen peroxide, but I prefer use periodate or persulfate, but it works very well, or permanganate as well. But,
thank you very much. Thank you.
No problem. It's a pleasure.
Thank you for your question, Eva. We have a question here from Johanna Cabrera. She thinks you had an awesome presentation, and she wants you to give her a little trick for fast curing with tannin adhesives. The trick for fast curing with tannin adhesives, would that also apply for lignin?
Yes, it would. Yes, it would. It depends on the formulation that actually you use. Yes, it would, because lignin has got the same problem. Lignin, is got a phenolic nature, but it doesn't melt. It melts, but but not very well. It's actually better than tannin from the point of view, but it will work with lignin as well. But the lignin is much more dependent from the formulation than tannin. Much more dependent. But if you want to use lignin, I think the best thing you can do is go for actually non-isocyanate polyurethane. It actually works quite well. Okay.
Interesting. We have a question from Erik Tybol. Can any of these systems be feasible for load-bearing applications?
Yes. What I did not show, in the presentation, because the time was actually limited, was one system that we use for finger joints and for laminated beams in South Africa, and then we tried in Chile, and it worked very nicely. This is called a separate application adhesives. They use with tannins. This, right? Now, what we do actually, we put a normal tannin resorptional formaldehyde adhesive on one side with a hardener. In the cases paraformaldehyde is still used, and on the other side we just put a tannin resorptional with nothing else but high pH. One is a normal pH, one is very high pH. And when you put the two together, both for finger joints or for beams, the curing is actually extremely fast. Within 2 hours, you actually got structural bearing material. In the case of beams, you need 2.5 hours. So we changed actually completely the industry in South Africa with that at the time. It was a long, long time ago, this, and it's still going. What happened before, the people were doing finger joints, they were doing beams, and then the customer was ordering the thing. So he was taking 1 week and a half before the order. There, the customer now can phone, the finger joints are done, the beams are done, and for the time the truck arrives, they put the material already ready to actually be installed for load bearing. It's a system. It's been 30 years that it's going in South Africa. This 30 years, and it works very nicely. Sorry, I didn't show that because I didn't realize if you were interested actually in cold setting adhesives as well.
You speak a lot about tannins here, and that's fascinating. And he's been there for a very long time, and still most of adhesives are fossil based. But you have showed several possible solutions, and some of them have been industrialized as well. And with your enthusiasm, why haven't we gotten further in this development?
But let me say to you, there is one of the big problems you never know, is industry in generally, likes actually to be comfortable with what actually they use. So if you actually have big companies, they actually use phenolic resins, MUF, UF resins, and they work very well. I worked on synthetics myself, not only on bio. So they work very well. So they hold the market. The question is, why change? Now, the situation is totally different. It's changed. Now, in South Africa, we started with that because there were sanctions against South Africa. It was actually a very good thing. It was a very good thing because it forced us to think biodiesel, because we couldn't import phenol at the time. That was the thing that was important. Now they produce phenol, so they couldn't care less. But, fundamentally now, with all the new regulation, the problem of emission of formaldehyde, the problem of phenol actually poisoning waters in the discharge, of phenolic materials, then there is a increased awareness, both in the public, in the user, of biomaterials that are going to be used. I give you an idea, for instance. There is a company in Germany, I will not mention it, that is actually using tannin adhesives, 600 tons per year, to make all sorts of things. They don't say that they actually are tannin adhesives since about 50 years. So they are used even in Europe. So I talk about tannin because I started my career in adhesives in tannins. Yeah, that's the reason why I stayed with them. But I've done all sorts of adhesive, both synthetics as well as other materials, as you see in the presentation.
Okay, thank you. Raffaello Papadakis, you have a question.
Yes, thank you. Thank you very much for a very stimulating presentation. I have one question with regard to the NIPU. The polyurethane that you produce is aminolysis of the carbonates that you showed. Can you compare the resulting polyurethanes to classic ones produced through isocyanates?
Look, the problem with the classic one, is a good system to have actually cyclic carbonates. It is no problem. I don't want to criticize it at all. The only criticism is that, in the wood industry, especially panel industry, we need a certain pressing time. They need actually to be fast. So see, if you actually use the system that you use, they're using a cyclic carbonate and diamines and things and nothing else, for instance, it can be natural as well. You actually got a pressing time that is not sufficiently fast for today's industry. We use an aliphatic carbonate. First of all, it's much cheaper. Second, you eliminate the step to form the cycle. So there's only one reaction less, or to form even worse, two cycles, because they're also bicyclic carbonates. So you eliminate the step, so it's much cheaper, it's easily available, it doesn't cost much, and it works much faster when you're actually trying to do the adhesives and pressing the adhesives, on the NIPU.
Thank you. I have another question also, if possible.
Please go ahead.
So you mentioned about hexamine reaction to phenolics, to tannins, and so on. And I guess this is a very nice example. But you mentioned that there is, of course, no formaldehyde emissions. But what about like amine emissions, probably through thermal decomposition?
Okay, hexamine is a very strange compound. Let me explain to you. I used it actually. I started to use it with Mosa, and then. As I show you, actually, the particularly reactive species, if it is well done, then there is no emission whatsoever. The problem is, at some time, the conditions that actually use to use hexamine are not actually ideal. And then you must actually have some formaldehyde that actually is created, that you like it or not. But in general, if it is well used and you are just at the very reactive species without actually going to formaldehyde, then you will have actually absorb even the formaldehyde created by the heating of the wood. And that is the trick. This is a trick, because you got no emission whatsoever, because you got no emission from the glue, and the bridge, CH2 and HCH2 is actually stable, to be up to 120 degrees centigrade. So you got no problem in service. And it absorbs all the formaldehyde created by the heating of the wood. So it's a trick. But it works, so you got no emission whatsoever. And that is, for instance, one of the systems they use in Japan with the steam injection, for instance. Sekisui Chemical Company is a big chemical company that actually owner of the biggest producer of wooden houses in Japan. That's it.
Thank you very much.
Thank you for your questions, Raffaello. We have a question here in the chat from Erik Tybol. Are there any challenges with shelf life of tannin-based adhesives?
But not really. But there is no problem with shelf life for a very simple reason, that you actually add hardeners or anything else only at the end. So the tannin itself, has got no problem. If you actually got it in the oven wet, the only thing is just to actually have stirring continuously, because it tends to lose water to the air and to form, a thick skin, let's say. Thick skin that is easily dissolved. There's no problem at all. But, otherwise, we actually prefer to have it spread dried in powder form. So you just put it in water, you dissolve it, and then you add any hardener or any other compound, like a proteins, for instance, when you want to use it. There's no problem whatsoever. No, there is no problem with shelf life because there is no hardness by itself.
Thank you for your answers. I don't have any more questions, but maybe we got some here now from Saman Gary. Yes, he has two quick questions. Since lignin dissolves in alkaline pH, how can citric acid, with its acidic nature, be used for lignin modification without causing its precipitation?
But if you don't if you can't use it actually with acid, because acid actually precipitates it, so that's it. So unless you actually hydrolyze it in different pieces, then you will have problems of precipitation that you like it or not. You got to be in alkaline in the case of lignin. So or you hydrolyze it, so you cut it into pieces, for instance, with the periodate, so but specific oxidation is called the reaction, or otherwise, you've got to actually be in alkaline state.
Okay. And the second question is, of course, a very interesting one for us all. What is your advice, kind of a roadmap for future research on bioadhesives?
But I would say, leave it simple. Because you can do all the publications you want. If it is not simple, industry will not be able to use it. It will not be convenient or economically, or it's too difficult to use. And when it's too difficult to use, you will have lots more problems than when it's actually easier to use. So keep it simple. Keep simple concept. That's what I actually presented in this presentation. You build on those if you want. You can do variations of the formulation. It's no problem at all. But keep it simple. The only thing that I can tell you. Otherwise, no one will ever use it.
Mm.
And be sure when you do a research to actually be yourself, if you develop something, to go on the floor of the factory and actually try it. Because there is nothing better than the bloke that has developed a system to try it in the factory to understand what are actually the drawbacks or the advantages of that particular system. I'm too old now to do it, but when I was young, that's what I did all the time. That's the reason why I was able to commercialize in several countries.
Thank you very much. I see that we have one question here still in the chat, and that could be the last one. Which are the most important quality parameters for spruce tannins to be followed?
Spruce tannin is a procyanidin tannin, so it is like pine tannin, pine bark tannin. It's actually quite good. I remember, there is someone in Finland that actually did some work together with one of my students, on spruce tannin, but it was only formulation at the level of the laboratory, and it worked quite well, like pine tannin. So you actually follow what is published on pine tannin, and you'll be able to use spruce tannin. There is no particular difficulty. The only problem that you might have too many carbohydrates actually in it. It depends from the percentage yield of extraction, what you got in phenolics and what you got in carbohydrates. I think it's a bit too high in carbohydrates, but that's quite easy. Or to hydrolyze the carbohydrates, or otherwise, you can go, from non-isocyanate polyurethane, with the a peroxide or some salt, and actually you will have the problem solved from the point of view.
Thank you very much. That was the last answer from Professor Antonio Pizzi. And I think we just give him a digital applaud here in the,
okay.
in the camera. And I think
it's been an absolute pleasure actually to present things that are actually reasonable to you people. Okay.
Yes. And I think we all agree with Alidori. Thank you so much, Professor Pizzi, for an informative and inspiring presentation.
Okay, thank you very much to all of you to have had the patience to attend. Okay, bye-bye.
Bye-bye. This presentation is recorded and will be published on the BioGlue Center YouTube channel shortly.
Torbjörn, see, if you want to other pictures or other things that were not in the presentation, like for the cold set, for instance, you just email me and I will send to you, okay?
Thank you.
No
so
problem.
thank you all for being with us in this webinar for an hour with BioGlue Center. And we'll arrange another webinar in a couple of months. So look out for that. Thank you very much, everybody, for participating.
Bye-bye.
Thank you, Tony.
Thank you. Bye.
Bye-bye. Bye-bye. Bye, Björn. Bye.
Bye-bye. See you later.